Yay!
Yay! One more example of a continuous charge distribution that we haven't done yet is the, well, I guess we sort of have, but it's the line of charge, but where you're not along the axis of the line. So here we've got a line that's L units long, charged up to plus Q. But now we're going to go up a distance y from the line of charge, and it turns out this is a pretty important example. We'll see it going forward quite a bit. And there's a number of ways that you could do it. This first time, let's just do the distance y being right above the midpoint of the line. So we'll do it that way, and then we'll do along a line right above one of the ends. We'll do that one too. But anyway, you should have a pretty good background in lines of charge by the time we're done with all this. All right, so let's see. How we get started is the same as always. Say the electric field is, it's the integral. What am I going to integrate? Probably I'm going to go from one end to the other. Let me leave the limits off for just a second. So it's going to be k times dq over r cubed r vector, right? We start kind of the same way every single time. What's going to happen is, let's see, we're chopping up this line into little bits dq, and each one is r away, like that, right? And then that's going to be my x, right? If r is the distance up to that point, then I got x to the right and y up is how I get there. So when you're in the middle, that x is going to be 0, right? So it looks like if I'm integrating along x, if I want that to be my integration variable, it looks like what I'm really going to want to do is go from minus L over 2 to plus L over 2 so that it's 0 in the middle. All right. And the next thing I want to do is change from dq to dx, so I have a good integration variable, because q doesn't go from minus L over 2 to plus L over 2, x does. So let's change, and we're going to change it the same way we did before. So a little bit of charge compared to the whole charge is like a little bit of length compared to the whole length. All right, so dq, this implies that dq is q over L times dx. Very cool. So now I can plug that in. So this is minus plus. I'm going to have a kq over L. And let's see, kq over L, I got my dq. That's going to be a dx over r cubed. Okay, so dx over, okay, r cubed. Look, as we're going down the line, that r is going to be changing, right? As we're going down the line, the distance up to that point changes. So I can't take it out of the integral, but I can write it in terms of x and y. That's what I want to do, because x is our integration variable. R is just square root of x squared plus y squared. So r cubed is just x squared plus y squared to the 3/2. Very cool. Let's see. Oh, and r vector. All right. So here we go. From that little dq, how do I get to, let's write our vector. How do I get to the point from that little bit of charge dq? I got to go to the right x, and I got to go up y, right? But then let's invoke our symmetry arguments. This is the way we've done the ones before. We're adding all these up, right? So in particular, I'm also going to add up that little dq on the other side. And that one, to get up there, you have to go minus x and plus y. So what's going to happen is when you add each of these dq's, and then eventually its little partner on the other side of the 0, the x's are going to go away. And you kind of know that, right? When you look at the problem, you sort of know that all the x components are going to disappear. This thing ought to only have a y component. So I don't even have to worry about the x's. They're going to go away. I'm just going to be left with that y. That's just the common factor of adding all these things together. So my integral is a q. The y doesn't change, right? The distance doesn't change up there from the line as I go across the line. So that's just a constant, kqy. I have an L. And then I got this, minus to plus. I got dx over x squared plus y squared to the 3/2. Okay, so that's my integral. I finally got it in the form of solving the integral. So what do? Well, your first whack at it is to try to suppose, let's see, could I let u is x squared plus y squared? Can I try that? Okay, well, if I do, then my du is 2x dx. The problem, I got my dx up there. The problem is I don't have this. I don't have that x, right? I can't just stick it in. It's not like a constant. That's an integration variable. So this is not an elementary form. I can't do that. This integral is not an elementary form. You might know, just looking at it, that this thing is probably a trig substitution, right? I think the way this form is, if it's x squared plus y squared, I think that's the secant tangent one. But in any case, I don't want to do it, right? You can do it in calc class, right? Or go look it up. Anyway, I'm just going to write down the answer. I'm going to look up the integral because this is about physics and getting the electric field. So here it is. In fact, this is a form, after you do this a few times, it may just stick in your head because we're going to run into this integral a lot. This is going to pop up lots of different occasions. So this is going to be, I got my k, q, y over L. And this integral turns out to be, let's see, it looks like it's x over y squared, x squared plus y squared minus L over 2 plus L over 2. Okay, there we go. So after looking up the integral, that's what we got. Okay, first of all, that y cancels with one of these y's. Nice. Let's look at it for a second. When I put in plus L over 2, look, that x on top, it's gonna be a plus L over 2 minus a minus L over 2 when I stick the bottom thing in there. So that's just gonna be an L. Okay, so I'm gonna do a couple of things at once. This is just gonna be a k, q over L, and then inside I'm gonna have an L. And then on the bottom, I'm going to have a y times the square root of x. Well, notice that it doesn't make any difference if it's plus L over 2 or minus L over 2 on the bottom for x because I'm squaring them, right? So let me flip the order and make this y squared plus L squared over 4. Okay, there we go. So now I've plugged in the limits. The L's go away. And it looks like, look, I'm done. This is my final answer. The electric field... Oh, I guess I didn't put that in. This is in the y-hat direction, right? So this is going to be kq over, the exact answer is y times the square root y squared plus L squared over 4. There we go. Don't we want this to look nice in a box? There we go. There we go. That's the exact answer. So for some distance y away from the midpoint of a line of charge, boom, we got the electric field right there. Oh, I guess I'll just write in y hat. Okay, no problem. One interesting thing is, let's check it. If y is a lot bigger than L, remember what should happen. If y is a lot bigger than L, then this line shrinks and it looks like a point charge if you're really, really far away from this thing. So if y is a lot bigger than L, then the y squared term in the denominator dominates. So sure enough, this just becomes kq over what, y times the square root of y squared? So it's y. So it's just kq over y squared. There we go. That's the electric field from a point charge, aq over distance squared. So sure enough, here's yet another form that in the limit looks like a point charge. It's kind of neat that a whole bunch of different functions all have the same limiting behavior. That's cool. A really useful thing to put in also, we're going to find out, is this limit. Y is a whole bunch less than L. This is called the infinite line approximation. Suppose you're so close to the line that it looks infinite, essentially. Then what do we have? Then this thing is, then the L squared term dominates, right? So I'm going to have a KQ over Y, and then it'll be the square root of L squared over 4. So that's the square, that's L over 2. So this is going to be L over 2. Well, the 2 just comes up top then. So it's 2KQ over YL. And then, okay, one thing to notice is, look, if you're close to the line, the electric field dies off as 1 over Y, 1 over distance. That's neat. We haven't, I think it's true, we haven't really encountered a field that dies off as 1 over Y, inversely proportional to the distance. It's always like for point charges, it's 1 over distance squared, or for dipoles, 1 over distance cubed, right? Or for a disk, it doesn't die off at all. It's constant. It's just a number. So this sort of fills in the gap. So now we know a field that dies off as 1 over Y. Cool. And also the way that we write it is, part of the problem is, it's sort of like we talked about with the disk. If it's infinite, if it's essentially infinite, what do I put in for the length? So instead, what we do is we just do the ratio of charge to length. That's a little bit easier when dealing with an infinitely long line, because really you're just interested in charge per meter. So this thing, charge per length, is what we call the linear charge density, lambda. It's a lowercase lambda. So here, the electric field is 2k lambda over Y. Great. Okay, so lambda is just charge per meter. Okay, so that's the electric field from a line. And then just real quick, let's do, just to sort of finish all these examples, let's do the electric field of a line of charge, except let's do, let me draw it a little bit further down. Let's do a point, a distance y away from the end. How about that? So this is still a length L, still charged up to plus Q. We're still going to divide this thing up into lots of little bits. dq, here's my x, right? So if we're over one end of the line, let's see how to set that up. Okay, so we start the same way. The electric field is integral of k dq over r cubed, r vector. Okay, now the limits. It looks like when I'm at one end, that x, the distance of our little bit dq up to the point I'm interested in, that's going to be 0, right? So the limits are different now. I'm going to integrate x from 0 out to L. It's the same dq. dq over q is dx over L. It's the same trick we used before. Okay, so let's plug that stuff in. So this is going to be 0 to L. This is going to be k q over L. Then I'm going to have my dx r cubed. Okay, so what is my distance? Same thing I had before. X squared plus y squared to the 1/2. Square root of that is r. I'm cubing it. So I get to the 3/2. And then I got my vector. Now, what's the vector? The vector from any of those dq's, what do I have to do? I have to go minus x, and then I have to go plus y. There's not going to be the symmetry that we had before, right? So I got to consider both of these things. I'm going to have an x component and a y component. So there we go. So that's what I've got. So what I'm going to have to do is consider these things separately. So let's do EX. So for EX, what I've got is KQ over L. I've got, oops. EX is KQ over L. Let's see, it's going to be minus, right? I got to remember that minus sign out there. I'm going to have 0 to L. I'm going to have X dx over this business on the bottom, x squared plus y squared to the 3/2. Now it looks like I can use a U substitution. So this is an elementary integral. This is a little bit more fun than using trig subs, so why not? Let's just do it. So U is x squared plus y squared. Du is 2x dx. Look, I've got that piece. I got my x dx. It's right there. So x dx is just du over 2. Okay, so all I have to do is just put my minus kq over 2l. This is going to be 0 to l. This is going to be du is on top, and then I got my u to the minus 3/2 on the bottom. So there it is. There's my integral. That's not so bad. U to the minus 3/2. What's the integral of? Let me just do some scratch work up here. U to the minus 3/2 du. What is that? That's u to the minus 1/2 over minus 1/2. You increase the thing by 1 and then put it over the thing. So that's going to be a minus, and the 2 comes up top. Well, look, that's going to be great because that cancels both the minus sign and the 2 that we have outside. So this is going to be KQ over L. 0 to L. And I've got what? Oh, 1 over the square root of that. 1 over the square root of the, oh, I've already solved the integral. 1 over the square root of the thing. So I've got 1 over the square root of x squared plus y squared 0 to L. Okay, so EX, the electric field in the x direction. Let's see, if I plug in L, I just get KQ, I just get, what, a 1. X squared plus y squared. And if I plug in 0, what do I get when I plug in 0? Oh, I'm sorry. The L goes in the bottom, doesn't it? Goodness sakes. KQ over L. And this is 1 over square root of y squared plus L squared. And then now when I plug in 0 for x in the bottom, plug it in for the right thing, then I get minus 1 over y. So I get minus 1 over y. That is it. That's the exact answer. There we go. So there's the x component of the electric field. And now let's do the y component. This is going to look pretty familiar. So let's go back up to the top, the general electric field. I just have my y, and as I move along, that's not going to change. So that's going to be dy is kqy over L, and then what do I have? 0 to L. Now I just have a dx over x squared plus y squared to the 3/2. That's the same integral that we just had before, so let's plug it in. KQY over L, and that was what? X over y squared, rid of x squared plus y squared. Rid of L. Okay. Again, one of these y's goes away. If I plug in L for x, now that cancels the L on the bottom. And when I plug in 0 for x, I get nothing, right? So all I have to really do is worry about the top thing. And so what I get is KQ over y is a square root of, oops, not x. Let me flop the order around, y squared plus L squared. And there we go. There's the y component. So in this example, notice that what we had to do, because there wasn't the symmetry that we had in other problems, we had to do both the x component and the y component, and we get different answers, right? So if you wanted to figure out what the magnitude of the electric field is there, well, you got a little algebra work to do, because you have to square the x and you have to square the y, and then take the square root of them, add it together. That's a little bit of a problem. But anyway, if all you want to know is the separate x and y components, well, there you go, if you're a distance up from the end of the line. Okay, next.